Alright, we're going to take a look at some real beams. Up to now we've been doing just what looks like textbook problems, but now we're going to look at what really happens in real steel construction. And so what you see here is a building that is an office building in downtown Indianapolis that has these steel columns spaced every so often. You've got then girders that go in between the columns, and then you've got the floor beams that frame into the girders. Right? Some of those floor beams are on the column line, but in between we've got these equally spaced floor beams that then support this metal formed deck, and on top of the metal formed deck is the concrete. That's what you're going to see down here below. That this is a drawing looking at the column here from the left. So we see here the flanges of the column here and here. We're looking at the web, and then this is one of these floor beams that frame in. This is a typical connection detail. And if you were to zoom in, these drawings these days are done at really tiny, printed at really tiny size. So to really get in here, you have to zoom in to find out that the typical connection detail is going to be through bolts of this beam into then the supporting member. And typically we're going to have 3 of those bolts. These are actually the holes, right? And in steel construction, the size of the hole is whatever the size of the bolt is plus a 1/16 of an inch for clearance, right? If it was exactly the same, you wouldn't be able to get the bolt through the hole. So you need a little bit of a space in there, right? And so we have a 6-inch gauge that totally from top to bottom in this 3-bolt connection. Right now, what happens here is there's a little tiny shear plate that comes out from the face of the column. It's going to be welded to the column flange, and then it goes into the web of the beam. And this beam here, here's our composite metal deck, and here's the concrete slab that's sitting on top of that. Okay, and so sometimes it's the prerogative of the fabricator whether they want to use a single connector plate or use a double angle connection, angle on either side. We're going to look at this as just a 3/8 inch connector plate, and we'll get into all this here just in a second. Right? So this floor beam then these are spaced every so often, and in our model they're going to be spaced every 5 feet. So that's coming in and out of the plane of the paper. They're under just dead plus live load conditions, what we call service loads, which is where we would check things like stiffness, not strength, but stiffness. Then we've got a total of 150 pounds per square foot of the floor area times this 5 foot coming in and out of the plane will give us then 750 pounds along the beam itself. And so our model of the beam is going to be a simply supported beam with just this uniformly distributed load. And in anticipating what's going to happen here units wise, that will be 0.75 kips per foot along the length of the beam. Now, why simple support? Because if we've got these 3 bolts in this shear plate, well, then that means there's got to be an ability to be able to transfer some sort of a force couple, right? And so here's the shear plate expanded out, and we've got these 3 bolts, and as the beam attempts to sag under this load, it'll rotate at the end, and that's going to shift the top bolt over to the right, it'll shift the bottom bolt over to the left, like so, and the middle one is probably going to just be in the middle. Don't really care too much about it. Right? That'll still be sort of a relatively straight line, because remember there's this clearance here that allows these bolts to move back and forth. And so wait a minute, how do we know? Because once those bolts are going to be in contact with each other, then there's a force couple at work here. There's a possible bending resistance just coming, or moment transfer through the connection detail. Is that a very significant value? And well, what the heck? I mean, how much if this was really a single bolt, how much, which would just be a pin, how much rotation would we get anyways, and how does that compare to what's capable of happening in this multi-bolt or multi-pin kind of arrangement? Right, so let's go and take a little closer look at our basic model here. Right, and so if we have a simply supported beam, then with a distributed load, then this rotation that happens over here at the left, we can go and we can either derive that or we can look it up in a table. It's a plus or minus expression, negative here on the left for a slope, positive over here for the slope on the right. But that's going to be theta equals WL cubed over 24 EI. Now at this point you should be able, in the beam deflection section, to be able to derive that, and that'd be a really good thing to do for preparation for the next exam. Where did that table value come from? But we're just going to work with it here right now. And so we've got 0.75 kips per foot for W. Now the length of this beam is 30 feet. That'll be cubed, and then divided by 24. It's steel, so the E is 29,000 kips per square inch. Now I can't tell you exactly what size the beam is because I have not gotten authorization from the owner to give you that information. But a typical beam size might be about a W18 by 35, and that second moment of area about the bending axis, IX, is taken for design purposes as 510 inches to the fourth, and the elastic section moduli is 57.6 inches cubed. Right, we want the I value, of course. So there's your 510 inches to the fourth. Now note the units we've got. In the numerator, we're going to have kip per foot times feet cubed, or kip foot squared, and in the denominator we'll have kip inch squared. So we want to get rid of that. I have 144 square inches over, then of course 1 square foot. And when we work this out, then note this is going to be a slope, or really, because it's going to be really small, right? Slopes are tangent of theta, rise over run, right? And we're going to find out that it is indeed very small. It is going to be 0.0082 radians, not degrees, but radians coming out of that. Right? That's not very big. So let's see what's capable of happening with the slop that happens in this joint. Right? There's a triangle that gets formed here. Right? Those bolts are initially all lined up over that 6 inches gauge. We have a 1/16 of an inch clearance, so the max that will happen here is a 1/16 of an inch, and how these bolts will kick over at an angle, right? And so there's your theta capacity here in our joint, and of course that's just equal to arctan of opposite over adjacent. Actually, that goes up here. And so 6 times 96 is, of course, 6 times 16 is 96. And so take the inverse tangent of that, 0.0104, and we're of course going to get back 0.0104, hence proving that we really are at small angles. And that's greater than what the demand would be if that was a perfect pin. That tells us here that pragmatically, right? So real connections, if the connection is made through bolts, then connection acts most likely like a single pin connection, just like we've done right here. Right? Now that's just based upon the bolts. What if this was a welded situation? Then it would definitely transfer moment through the connection. Well, let's take a closer look at that. Right, we can do that. Let's look at what the flexural capacity of the beam is, and we're just going to do this in a very simple kind of way. These days, beams are typically going to be of grade 50 steel. That means our sigma y equals 50 ksi. Right? So our model here for the flexural capacity, just let's use the yield capacity, so that would be sigma y times s for the bending axis. Right? So for us, that's 50 kips per square inch, and our s for the bending axis is 57.6 inches cubed, and of course that means we're going to get something in kip inches. So for kicks, I'm going to turn that into kip feet. So 50 times 57.6 divided by 12 would be a basic yield moment of 240 kip foot. Right? Now what we're going to be transferring that into in terms of the plate, the shear plate, if we try to transfer the whole capacity of the beam through the capacity of this shear plate, note here that we've got a shear plate that is 3/8 of an inch thick, and we know it's at least 6 inches high. And indeed, where's my drawing here? Let's see if it tells us on the drawing. If not, I'll give you an educated guess about how high that might actually be. Yep, 6 plus 1.5 to the outside, so that's another 3. So we're at 9 inches tall. Right, so we had standard typical dimensions here. We had those holes at 3 inches apart for the bolts. Right, that was here, here, and here, so 3 inches in between, and then another 1.5 inches, so we had a total 9 inches. And we're interested in what the flexural capacity of this would be. Doesn't matter what direction the moment would be, but a moment either way, how much could that possibly handle? Right? And so that's just a yield moment there. The cross section that we're talking about is just a rectangular cross section, where there's your bending axis. That's of course 4.5 inches high. It's at the midpoint, right? And we know that the S for this is 1/6 BH squared, right? 1/12 BH cubed is the I, and your C, of course, is H over 2. The ratio of those two will give us the S. That's where we get the 1/6 BH squared. Right? So once again, our yield moment or capacity for the plate takes sigma y times s. Now, typically, this would be made out of a A36 steel, not grade 50. And so sigma y here would be 36 ksi for the plate. Right? Common garden variety steel plate hanging around, waiting to be used in the shop. And we'll find that that's going to be 36 kips per square inch times our S, which is 1/6 of the base, that's the 3/8 inch, times our height squared, that's 9 inches, and then of course do the same conversion of units, 1 foot over 12 inches. And look how much smaller this is going to be here. We have 36 divided by 6 times 0.375 times 9 squared, which is 81, divided by 12, and that's only 15 kip foot. Right? Now you might say, well, what if this had been 50 ksi? We could have. It wouldn't have increased this very much. What if the beam was old school and it was A36 also? Well, that's not going to change this very much. The plain blunt reality is that the moment capacity of the beam is much greater than the moment capacity of this connecting plate, right? And not just a little bit greater, it is much greater. What that says is that in real beams, with only a web connection, the connection acts like a pin, even if it were fully welded up, at least in the web only here, right? So that's the key, only a web connection, right? Because most of the beam's moment sorry, had to turn off the phone there. Most of the beam's moment is carried via its flange, right? Think sigma equals my over I. If the flanges, that should be its flanges, if the flanges are not connected, not much moment can be transferred. Right? And that's going to be the key to something that we talked about quite a while ago, and that is that when you're making basic models of beams, you want to look at, well, is that a fixed connection transferring moment, or is it one that is transferring only shear? And it's all about, is the web connected, and is the flange connected? Shear goes through the web, and it's really shear and axial for the most part anyways, via web. Moment via the flange. Right? And that's how we begin to make those basic models from real stuff into what we're doing here in the classroom.